So let's start commutative algebra. Commutative algebra basically is the study of commutative rings, ideals of this type of rings and modules over such rings. Besides being interesting in their own rights, these things are studied because they are needed in two other areas of mathematics, two other branches. One of them is algebraic number theory, and the other one is algebraic geometry. These areas provide us with the objects that we study in commutative algebra, namely these commutative rings and the other things associated with them. Now, the prototype of commutative ring that we get from algebraic number theory is our familiar ring of integers. And the type of ring we get from algebraic geometry are the polynomial rings in several variables, that is these rings. Where these are the indeterminates or variables, if we want to call them so, and K is a field. So you already know what these, what the objects in this type of rings are. They are polynomials in these indeterminates and the coefficients are coming from the field K. Alright. So that's what commutative algebra is all about. It's mainly a study of commutative rings. Now before we start, let us fix some notations. We are going to write a mapping. Say f is a mapping, a function from some set A into B. Then for any element x in A, we are going to denote the image of x under f like this, which is what we usually use. This is the more common notation. This means that we won't write this image as xf. This is another way of writing the image, which for example is followed in Herstein's topics in algebra. We are not going to write like this. And that is why if you have another function, if you have, say, besides this function, say you have another function g from B to C, then the composition of f and g is written as g composition f. The reason, of course, you already know. It is that since we write mappings on the left according to this notation, so when you apply g composition f on any element x of A, it makes sense. Why? Because this is the g image of the f image of x. Instead, if you use this notation, then that same composition will not look like this. In that case, if this notation is followed, you would have to write f composition g. Why? Because if you apply f composition g on an x coming from A, then since you are writing mappings on the right in that notation, so it makes sense, because now see again we are applying f to x first and then to the image we are applying g. Okay, so when you study a book in mathematics, which of course, everywhere There is rarely any book in higher mathematics where you won't get function composition. You have to be absolutely sure about which of the two notations is being followed, so that you do not run into any kind of confusion. Here we have the usual notation, and that is why when we compose f and g, the order gets switched, g followed by f, because the application happens from that side first. So that is one thing. And the other thing is about the inclusion relation or subset relation. That is also something about which we should say in the beginning itself. If you have followed Herstein's topics in algebra, there we write like this to mean that A is a subset of B. That means this notation means the subset relation between sets in Herstein's topics in algebra. However, in this book, we write this to mean the same thing. We use this notation instead, which clearly indicates that the option for A and B being equal is also being shown. So this notation is like, it's exactly the same notation that Terence Tao follows in analysis, in his book Analysis 1. However, to mean the proper subset relation, Terence Tao would write like this. That is, A is a subset of B, but A is not equal to B. In this book, however, in Atiyah's book, this same proper subset relation is written like this. This means proper subset. So it's like, writing like something like this. Say x and y are two numbers. This means x is less than or equal to y. A is a subset of B and A may be equal to B. Whereas if you write like this, it means that x is actually less than y. X cannot be equal to y. So just like this notation, you have this notation. A is a proper subset of B. A is a subset of B, but A is not equal to B. A is properly included in B. Besides these notations, these are of course our usual sets. Z denotes the set of all, or rather I should say the ring of all integers. Q denotes the field of all rational numbers. R denotes the field of all real numbers, and C denotes the field of all complex numbers. So that is all our notations. All our notations means the initial ones that we need to know about to start. And now we are going to start. Alright, so in this video we are going to just see rings and ring homomorphisms. In fact, this first part of the book, first part means this first chapter, is going to review the things from ring theory that we already know. So let us first see the definition of rings. You are of course supposed to already have gone through ring theory once, and not just ring theory, group theory also. And a general first course in abstract algebra is a prerequisite for this. So this is how the authors define a ring. A ring A is a set with two binary operations. which of course are called addition and multiplication. Such that these are true. Number 1, A is an abelian group WRT with respect to addition. You already know what this means. So these things of course are there. So there is a 0 element in A, I must mention, denoted by our usual notation 0, and each element x in A has an inverse with respect to addition. To indicate the fact, to emphasize the fact that this is an inverse with respect to addition, we call it additive inverse. Which we denote by minus x. So the usual stuff that we have in an abelian group are true in A, because A should be an abelian group with respect to addition. This is one condition, one requirement for A to be a ring. The second requirement is that multiplication is associative. And the authors write that this means x y times z is equal to x times y z, where of course it's understood that x, y and z are elements coming from A, and distributive over addition. This means that the two distributive laws are true, which itself means that for any three elements x, y and z coming from A, not necessarily distinct, they may or may not be the same, x times y plus z is xy plus xz, and also y plus z times x is yx plus zx. Okay, so if these two conditions are true, then we call the system A. System A means the set A with the two binary operations addition and multiplication a ring. However, see, as we see these things, because we have seen similar things in topics in algebra by Herstein, so as we go along, as we see these things again, we are going to parallelly see and recall what we saw in topics in algebra. So far, is there anything different from what we already know what a ring is from topics in algebra? No. This is exactly what Herstein would also call a ring. An abelian group in which there is also a multiplication operation and that multiplication operation is associative and the two distributive laws are true. However, although we are calling this system a ring, but we are going to in fact look at a special class of rings only in commutative algebra, namely commutative rings. We won't consider non-commutative rings at all here, whereas in Herstein we did consider non-commutative rings also. For example, we saw examples of matrix rings which are non-commutative rings. So, we are not concerned about non-commutative rings here. We are only going to consider rings that are commutative. What that means is this, that xy equals yx for all x and y coming from A. In other words, multiplication operation is commutative, and additionally that are commutative and have, I could have written and here also, and have an identity element. We require this as well. We are only going to consider rings which are commutative and have an identity element. And what does that mean? What do we mean by an identity element and a ring having such an element? It means this. There exists an element which we denote by the symbol 1 in A, such that x1 equals 1x equals x for all x in A. And this element is unique. Is then unique. We are going to make sense of absolutely everything we see in this book, okay? Either by verifying it or by indicating where we can find a verification and recalling such a verification if we already have seen it elsewhere. Although we have already seen in ring theory how an identity element is unique when it exists. I mean, when we studied ring theory in Herstein's topics in algebra, there itself at some part I showed, but I can't remember clearly. So that is why let us see now again how this is unique. And for that, I will just draw this dashed line. Whatever happens within two dashed lines, that's only for our own understanding. Say you have a ring A which potentially has two different, potentially I say because we don't really know. Say a ring A has two identity elements. One of them is 1 and the other one is 1 prime, because both of them are identity elements. So for both of them, this condition is going to be true, that is x1 will be equal to 1x, that will be equal to x, and also x1 prime is equal to 1 prime x, this is equal to x for all x belonging to A. Alright. Now look at the first chain of equalities. These are true for any element x in A. In particular, I can take 1 prime in place of x. I can. So that way I will get, if I put 1 prime here, I get 1 prime 1 is equal to 1 prime. I am using the fact that x1 is equal to x with 1 prime in place of x. So this is one thing. But at the same time, now let's look at the second set of equalities. Here, these are also true for all x belonging to A. So in place of x, now if I take 1 and use the fact that 1 prime x is equal to x, what shall I get? I will get 1 prime 1 is equal to 1. So 1 prime 1 is simultaneously 1 as well as 1 prime. Can there be two different values of 1 prime 1? No. Why? Because multiplication is a well-defined binary operation. So when you take two elements from the ring and combine them through multiplication, you are going to get a unique element, and that is why 1 prime is equal to 1. And that way, whenever there is an identity element, that must be unique. Okay. So we are only going to consider this type of rings, which are commutative and which have an identity element. Now let us also recall that we have already considered this type of rings in Herstein's topics in algebra. But the slight difference is that what we are calling an identity element, Herstein would call a unit element in a ring. The names are different, but the object is same. What Atiyah calls an identity element, Herstein would call a unit element. So it makes sense to not write every time you want to mention that you are dealing with a ring, a commutative ring with identity element, a commutative ring with identity element. It becomes unnecessarily cumbersome. So instead, we are going to decide to call this type of rings ring itself. Okay, so that's why the authors next say in this text or throughout this text, the word ring means a commutative ring with identity element. And this is why, again, when you start studying some book in algebra, this type of things may confuse you if you neglect the first discussions. If you do not carefully read the first discussions, then you will not get this ring. So what will happen is that, say you know by ring, you know that whatever you have in topics in algebra, say, you know that a ring is just simply a ring. You forgot to see that in this book, we only mean by ring a commutative ring with unit element. Then whenever you see this word ring, it will just simply be confusing to you. Forever it will confuse you. Alright. So that is our setup. And then there is a remark. The remark is about the identity element, its nature. In 4, we do not exclude the possibility that the identity element 1 might be equal to the 0 element 0. Now this is possible, in some situations this is possible, that the identity element is equal to the 0 element. It sounds very strange, but it should not be so strange for us who know a little about abstract algebra. And it looks also very strange. That is, we may have 1 equal to 0, but we know that this 1 is not the real number 1 and this 0 is also not the real number 0. This is an identity element and this is the 0 element in a ring. In fact, in that case, for any element x in A, we would have this. X of course is equal to x1. Why? Because 1 is an identity element. This is what identity elements do. But now the identity element is also the 0 element, and you know from elementary properties of rings that whenever you multiply a ring element by 0, you get 0. So in such a ring where 1 is equal to 0, the only element is the 0 element. And in fact that element itself plays the role of an identity element. Thus, A is the 0 ring. Ideally we should write the 0 ring like this, because after all it's the set. Or sometimes we write like this also, but by abuse of notation, because it will quickly become cumbersome to keep writing these brackets. We will simply write 0 to mean the 0 ring. By abuse of notation. Something is an abuse of notation when you do not write the notation fully. Instead, you write some simplified version of the notation. Will it not create any kind of trouble later, any kind of confusion? See, you may think that just by looking at 0, you may confuse it for a real number, or you may in fact confuse it for the identity, 0 element. But the main thing is the context. Whenever you are having a discussion and say you come across a ring R and there is a statement like this, obviously this 0 cannot mean the 0 element. If we are saying that this ring is equal to 0, definitely this also has to be a ring. So in that case it will mean the 0 ring. So usually from context you will be able to figure out whether this 0 means the 0 element or the 0 ring. That is why it's okay to abuse notation and discard this brackets. Next we go to the notion of a ring homomorphism. The zero ring is also considered by Herstein in topics in algebra, and in fact it has caused much pain because Herstein every now and then won't really be careful to simply not consider the zero ring in many statements of theorems, which causes problem, but that is something else. Okay. So next let us see ring homomorphisms. A ring homomorphism, again keep in mind, for us ring means a ring that is commutative and has an identity element, is a mapping F from A to B, where A and B are rings such that, number one, there are three conditions. You may wonder why three conditions, because normally when we talk about homomorphisms, ring homomorphisms, we have only two conditions. The first one, of course, is this: f of x plus y is equal to f of x plus f of y, where obviously x and y are coming from A, but still let me write for all x and y belonging to A. So you can see that if we just simply think of this condition, then f is a homomorphism of abelian groups. Which abelian groups? The abelian groups A and B under addition, because being rings they are also additive abelian groups. So this condition alone tells us that F is a homomorphism of abelian groups, and as such we have these things. That is, whatever properties we know of group homomorphisms, they will be true for F. For example, if you apply F to the identity element of the domain group, then you get the identity element of the codomain group. Identity element in the sense of group theory, okay, not in ring theory, I mean the zero element. Also, applying F on the additive inverse of some element or the group inverse of the element X in the additive group A plus is this. Similarly, you also have this identity. So whatever we know about group homomorphisms are true for F. Number 2, F behaves well with multiplication also, just like it behaves well with addition. Further, obviously at this stage it does not make sense to again comment on the fact that this plus is the plus in A and this is the plus in B. You already know these things. for all x and y belonging to A. But what can be the third condition? The third condition comes from the fact that the rings have identity element. So F needs to respect this identity element as well. Identity elements, I should say rather. If you apply F on the identity element coming from A, you should get the identity element coming from B. Sometimes, in order to distinguish these things, some people would write like this. This indicates that 1A is the identity element in A and 1B is that in B. Similarly, you can write like this. This is the 0 element of A and that is the 0 element of B. But again, this is the actual complete notation, but we abuse notation because from context we would know which one is which. Why? Because F is a function from A into B. So if I write simply 1 here, obviously I would mean 1 coming from A. That is why we do not normally write these things. But if there is a chance of confusion, then we write the full notation. Okay, now a comment on this about comparing this thing with the definition of homomorphism, ring homomorphism that we saw in Herstein's topics in algebra. What would Herstein define? I mean, say Herstein also considers this type of rings only. I mean, that is also allowed. Say A is a commutative ring with identity element and so is B. And F is a function from A to B. According to Herstein, F would be called a homomorphism if just a ring homomorphism, if just conditions 1 and 2 are true. He doesn't care whether condition 3 is true or not true. And that is why ring homomorphism for Atiyah and for Herstein are actually two different things. Atiyah's ring homomorphisms are more special in this sense that they also have to satisfy this third condition. So keep this in mind. We are carefully going to compare everything between these two books because the other one we have already seen and this is the one we are again seeing. And then comes the notion of a subring, and unfortunately here there is a mistake in the book. A small mistake, but it's a mistake nonetheless. A subring S of a ring is I need to write the ring of a ring A is a subset of A that is a subgroup of A under addition and is closed under multiplication. So you have a ring A and you have a subset S of A. We would call S a subring of A if S is a subgroup of A. There are two conditions. S is a subgroup of A under addition, and then the second condition is that S is closed under multiplication. The error in the book is that the book states that such a subset S is a subring of A if S is just closed under addition and multiplication. Simply being closed under addition is not enough. Let me give you one example. Consider the ring of integers. Actually, there is another condition also, because I got so caught up about this mistake that I forgot to mention. There is one more thing that needs to be satisfied by S. S is closed under multiplication and S contains the identity element of A. Okay, so let's now see that example. Let's consider the ring of integers, right? Now, in the ring of integers, you have the subset of natural numbers. Whether you want to call the set of positive integers the set of natural numbers, or you want to include 0 in n, it does not matter. Say for the sake of being definite, I assume that 0 is included. So this is the set of natural numbers we consider in Terence-Strauss analysis. Now, is the set of integers a ring in our sense? Yes. Why? Because it's already a ring even in Herstein's sense. Is it commutative? Yes. Is there an identity element? Yes. The ordinary integer 1. Okay. Is this set closed under addition? Yes. Whenever you add any two natural numbers, or more specifically any two non-negative integers, you again get a non-negative integer. Is it closed under multiplication? Yes. The product of any two non-negative integers is again a non-negative integer. Does it contain the the identity element of z, which is 1? Yes, that is also true. But is this a subring of z? No. You won't really want to call it a subring of z. Why? Because this is not a ring. This lacks additive inverses, for example, although it does have the 0 element. So that's a little mistake. It needs to be a subgroup of A under addition, has to be closed under multiplication, and must contain the identity element of S. Then only we call it a subring of S. In Herstein's topics in algebra, the notion of subring really hasn't been, he doesn't even mention, I think, the word subring. It's not really given any importance. In fact, the only kind of subsets in a ring that Herstein considers are the ideals. We will also study ideals, but subring also has been mentioned here in a slightly wrong way. Now, if S is a subring of A, then the identity map from S into A is a ring homomorphism. This identity map, actually the authors call it identity map because of the rule that it has, that any element you take from S and apply the map on it, it remains the same, it does not change. So that map, let me just use the Greek letter iota to denote this map, is this mapping actually. And its definition is of course this. Say you take an element smallest from S then it just does nothing to S. It keeps S the same. Normally, this map has another name, which is the more common one that is used. It's called the inclusion map. It just, in a sense, it includes the elements of S inside A. I mean, of course, already S is inside A, but this is emphasizing the fact again that the elements of S are inside A, or that S is a subset of A, by re-emphasizing that whenever it applies itself to any element of S, then that we get that element back. And that element, because this is the mapping from S into A, is again in A. Because of this fact, this notation is sometimes used, that S is inside A again. Okay, so this is sometimes called means this is the more common name, inclusion map. So what the authors are saying is that this inclusion map or identity map, whatever you want to call it, is a ring homomorphism. Let's see how. Actually, this is very easy, but again, no matter how easy something is, we are going to see everything in absolute detail. That way we can be sure all the time that we are correct, that we haven't misinterpreted anything and we haven't likely made any mistakes anywhere. So what do we need? First of all, S and A both have to be rings. Are they both rings? A already is a ring, and S being a subring of A is itself a ring. Okay. Now let us take two elements S1 and S2 in S and apply the inclusion map on S1 plus S2. Because S1 and S2 are elements in S, S1 plus S2 is again an element in S, and by the definition of iota, this is simply S1 plus S2. However, again, because S1 and S2 are elements of S, S1 is iota of S1 and S2 is iota of S2. So yes, iota satisfies the first condition. In a similar manner, S1, S2 is also an element of S, so applying iota on that gives us S1, S2, which is this. So iota satisfies the second condition as well. And finally, what about this? By definition, this is 1. However, does this make sense? Is 1 in S? Otherwise, this symbol is meaningless. Yes, it is in S. Why? Because S is a subring of S. So by the definition of a subring, 1 is in S. And that's why we can apply iota on 1. This symbol is not exactly like this. It's somewhat like this. So that is why it really is a ring homomorphism. In a similar manner, you can verify this, and I leave the verification to you. If from A to B and G from B to C are ring homomorphisms, then so is their composition. how will you write the composition? Because we are using the usual function notation. If you compose f and g, you have to switch the order. G composition f. So this simply means that A, B and C are rings. The type of rings we are considering, that is commutative rings with identity elements. And let me just stop here itself. In the next video means next Thursday, we are going to see ideals and quotient rings, and then there are many more things. So that's just it for tonight. And tomorrow we have, what do we have? Calculus. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Group. Have a nice day.